So we'll do some simple examples using these quick ways of drawing the shear force diagram and the bending moment diagram. So let me run through these. What we're going to do is the main types of beam you'll come across. We've got simply supported here, pinned one end, roller at the other. We've got a cantilever, and then we've got an overhanging beam. And the beam might overhang at both ends, but we'll just do overhanging at one end. There's a couple of reasons for doing this. One is just to practice what we've learned without it being too complicated, so you get lost halfway through. The other reason for doing it is it's a good idea to try and kind of half remember these the shapes of the shear force diagrams and the bending moment diagrams for these simple cases. And I'll also highlight a few tips and tricks as we go along as well. And what that'll do is a lot of the time when you're actually on site, when you actually need to use this sort of thing, they will be very simple examples, what you need to calculate. And so it's having a good idea of these simple situations and having a picture in your head before you even start is really useful. Also, it'll act as a bit of a sanity check when you're doing more complicated examples. Some of the features of these simple cases will carry through to the more complicated cases, and they'll help you see when something's probably gone wrong. Okay, so let's just start with A. I'll do each of them in turn and save it as a video. If you're here without having tried this first, go back and try it. Try it yourself first before you start looking at this video. Maths is like that, or this kind of engineering with when you're actually calculating numbers is like that. You learn nothing just by listening to me talk. You need to go and try the example first. If you get stuck, come and look at it, but try and finish it as best you can, and then come back and look at this and see where you went wrong, and then you'll remember it. But you won't remember it it's harder to remember it if you just watch this without having tried it yourself first. So first thing is always to find the reactions. We've got a point load, it's going to be dead simple, so I'll quickly run through that first. Well, first thing is to draw a free body diagram. So I'll draw my free body diagram, think about what reactions I'll get at each support, and then I'll calculate those reactions. And for all of these examples, there's no X component in any of these forces, so we're not going to have an X component at this pin connection. It's just going to be two Y components. I'm not even going to bother writing down about the X component now. Okay, back in a minute. So I've got my reactions. So at this time, probably should have done this more often in the past, but I've just taken the moment rules first. So we've always got three rules. Some of the X components is 0. That's why I know there's no X component in the reaction. Some of the Y components is 0, and the sum of the moments about any point is also 0. And so what I've done first is taken the sum of the moments about A, and that's let me calculate RB. Then I've taken the sum of moments about B. That's let me calculate RA. And this time, because I've used the sum of the moments about both ends, what I've done to check it is I've just checked that those reactions add up to the applied force in the opposite direction. And therefore, we get the sum of the Y components is 0, which we must have. If that wasn't 0, I'd made a mistake somewhere. We could also take in the sum of the moments about C. It's another way to check it, make sure that works. Should 4 times 2 is 8. Oh, sorry. 6. So it's 6 times 2 is 12, that's RA. And then we've got 3 times 4 is also 12, so that would also be 0. So heaps of different ways to check whether your reactions are right. So now we've got the reactions. What I might just do is just rearrange this. It's nice when you get all the diagrams lining up. It just saves you, means that you can see everything in one go. So I'm just going to bring this across here, so we can see it, and then we'll put the calcs for each stage beside the appropriate diagram. Okay, so now we're going to be working on the shear force diagram. I just have to bring it down a fraction. Let's just put it here. So I'll just sketch my axes first. So for shear force, it's positive upwards, and then I'll come back and we'll just go through the shear force diagram. So let me just do that, 2 seconds. So I've drawn my axes. So shear force diagram, you get it from your free body diagram. You should really label each of these. So let me just shuffle this up a bit. And we'll just write FBD for free body diagram. and then SFD for shear force diagram, and the symbol for shear is V, capital V. So we just follow the forces. So we start at 0, and then we're going to just follow the forces. So we're going to go up. RA is 6 kilonewtons, and so we're going to go up 6 kilonewtons. Draw it on. Oops. Then it's going to go horizontal till it gets to the next point load. Then it's going to go down 10 kilonewtons, so down to -4. And then it's going to go along to the next point load, and then it's going to go up. RB was 4 kilonewtons, which takes us back to 0. So we can be fairly confident we've got the right answer. So we've got the right shear force diagram. Now, I'm already thinking ahead, so I'll shade this in this one. Just shade it. So we should shade or hatch it. So we'll hatch that. And usually we just write on the values. It just makes it easy for people to see. So that's 6 kilonewtons, that's -4 kilonewtons. Something else, so I'm thinking ahead to my bending moment diagram. And I'd be thinking there that I've got 0 shear here, so that should be a local maximum or minimum for that bending moment diagram. I wonder if I did the right thing by putting these vertically. I wonder if it would have been better just to keep them horizontally. Okay, I might change that back, and then I'll draw my moment axes, remembering that moment is positive downwards, and then we'll figure out the moment diagram. Okay, so remembering we're coming from this originally, it's all point loads, and so that tells us a bit about the shape of the bending moment diagram. If it's all point loads, it should all be straight lines, the bending moment diagram. They're not going to be horizontal, or they're not necessarily horizontal like the shear force diagram was, but they will be straight lines. It's only when you get line loads that you'll start to get curves involved. Okay, and so easiest way to do it, so you're always remembering the change in bending moment is equal to the area under the shear force diagram. That's all you need to remember. Everything else comes from that. So we could do it stepwise. For every 1 meter we go along, we're going to need to go positive, because it's a positive shear, positive 3 kilonewtons. So this is, sorry, positive 6 kilonewtons. This is 6, this is 1, distance of 1 along, so we're going to have to go positive 6 kilonewtons. And I was trying to pre-guess what these would be. So in fact, that would be 12 kilonewtons down here. And so we're going to get a bending moment for every, not too easy to draw, so that would be 6 here. So for every 1 meter we go along, we need to go 6 times 1, 6 kilonewtons. Alternatively, we could just go right to the end of this part of the shear force diagram. We could go to 2, so we'd do area under the shear force diagram is 6 times 2, which would be 12 kilonewtons. And we can draw a straight line. So if it was let me just draw it first. That's fine. Then we're thinking, okay, now we've got a negative shear, so we're going to be going in the negative direction on the moment diagram. Negative direction is upwards on a moment diagram, positive is downwards. And for every meter along, we're going to go 4 times 1 meter, 4 kilonewtons in the up direction. Or we could go the whole way along. We know it's a straight line because this is a rectangular shear force diagram. And so we just do 4 times 1, 2, 3. 4 times 3 is 12. And so we're coming back to 0, which is what we'd expect because it's pins at the end of the beam. The rule for moment is 0 is only true if that pin is at the end of the beam. And so we should come back to 0, and we'll just write on this value here, moment is equal to 12. This is all kilonewton meters, it's all moments. So moment is equal to 12 kilonewton meters. And then just shade that in. And we can see the peak moment is at 0 shear, which is also directly under the load. Okay, so you're always going to get, if you've just got point loads, your peak moment's always going to be under one of those loads. Now, so that's us drawing those. I don't really like how I've done it. I'll just quickly tidy up that bit, the shading on that, and probably the shading on the shear one as well. And then we'll come back and we'll just check one point. So we'll choose a point and check it and make sure we've got the right answer using the method of sections. So I've just drawn the section, and what I've done is I'm taking a section at C, but it's just before that point load, so I don't have to draw on the point load, and we can calculate from that. And so casting our minds back to how to do method of sections, and so we just drew out the beam, cut it to reveal the internal forces, make them kind of pretend external forces. The only time when we use the rules about the positives for the internal forces is when we're putting these on. So our positive shear is this way, so we're down on the right hand side, positive moment is this way, and so we're going anti-clockwise for MC. Okay, and so let's just use the rules. We've got no x components, but we're just making sure it's got static equilibrium. So the sum of the x components is 0, but there is no x component, so everything's 0. Sum of the y components must be 0. And so now you're switching back to the usual conventions for positive and negative. And so we're going up. So we're going up 6 kilonewtons, and then we're going down VC, which is equal to 0. So therefore VC must be equal to 6 kilonewtons. And then we're checking that against just before we get to 2. Correct. We've got V is equal to 6 kilonewtons. And once we get to 2, it suddenly drops because of that point load. Then the other rule we've got is the sum of the moments must be equal to 0 about any point. But we'll take it at C. So let's just see what we're doing. Sum of the moments about C must be equal to 0, and so let's just go through those. We've got 6 kilonewtons times 2 meters, so we've got 6 times 2, and it's going clockwise, so it's negative. Then we've got MC is anti-clockwise, so it's positive, so plus MC equals 0, so MC is equal to 12 kilonewton meters, and that's what we've got. So at 2, MC is 12 kilonewton meters, and so we've checked that and we know we've got the right answer. You could check any point you want and make sure you've got the right answers. So this is always there for checking.